So today we have seen many processes related to bottom currents and the water masses that drive them. And right now I will show you a little bit what happens when those currents interact with a different type of currents that have been mentioned here today as well, which is gravity-driven currents, so gravitational flows. So as many of you already know this, bottom currents tend to be baroclinic flows. They can also be barotropic. But what does that mean? Well, a baroclinic flow is driven by density contrast. So its salinity and its temperature is quite different from the surrounding water masses. And you can imagine this as a plunging water mass that comes, for example, from a more constricted basin or even from the poles. And that's why it's very different, significantly different from the other water masses that are in the ocean. So when it plunges out, it will have an horizontal front, and it will have such different characteristics that it's capable of flowing around the slope and conjuring at different depths. And that is why these currents are capable of not only winnowing, but also reworking and depositing sediments as well. Sorry, there is a message here. Okay, all good. But what happens when we start to deposit these systems? Well, we have seen that they have many features, both depositional and erosional. So you can see, for example, in this example, that they can create drifts with different shapes, but also erosional features such as channels, such as terraces, and others. So what ends up happening is that with the passage of a water mass during several million of years, or even thousands of years, we end up developing a contrite system. And so that system can have, as you see here in the seismic, many features within it. And here you have, for example, the terrace that you see here in this model as well, the more muddy sediment, which forms a drift, and even intercalations with other types of deposits as well. And this is all related to the energy and to the differences of the main water mass that has taken the sediment that is forming this system. But now, on the other hand, we have gravitational flows. And gravitational flows can be quite different. As most of you know, they can be cohesive flows. They can be non-cohesive. They can be laminar, which is slightly more rare, or even turbulent flows, which is the most common that you see in most systems, as is represented here in this model. They can be hyperpycnal or hypopycnal. And what that means is, for example, if they are hyperpycnal, they can be quite dense and quite heavy with sediments when they flow down slope. If they are hypopycnal, their density is less than the surrounding water and the water that they flow through. So they will flow along in between surfaces rather than along the bottom of the seafloor. For example, in this experiment done by Snow and Sutherland, we have a representation of such a flow. And you can see here that this turbidity flow in particular is hyperpycnal because it's much denser. It flows down along the slope, and you can even see the shape of the main body, the head, and the turbulent clouds and the billows that it forms. So this is a much quicker, much faster process than the bottom currents that we saw previously. In addition, the types of systems that it forms, some people might think that it may be different from contrites or somewhat more similar. But what you see is mostly that it has a source to sink system. So it has a point of entry. For example, it could be a river, such as the case here shown in the Congo fine example from colleagues from Aspiros Azabala. And you have the river of the Congo, which provides a lot of the sediment through the Congo channel, the Congo Canyon, and then it deposits fans later on. And here you can see many of the morphologies that are formed by those flows when there is some discharge throughout. And they can be quite sinuous channels, but also you can have depositional features as well, such as those that we mentioned before. So you can have, for example, turbidite levees laterally. They are represented here in this model, or even channel lobes if it's at the end of the system and they are part of the submarine fan, so it's more complex. So you have two types of processes that occur on deep marine settings, but of course the deep marine system in a deep water environment is not a strict, is not a confined environment. So the two processes will often interact. And what happens when they interact? Well, you could have the processes interacting synchronously. For example, in this model, we have drawn here several channels along with several overbank features along this tributary network that goes towards the channels, but also you could have a bottom current that sweeps through them. And when you have the turbidity flows flowing downslope, the bottom current that is flowing throughout this area at a very specific water depth, it can take some of the sediment that is being carried, not only in the turbulent cloud, but even some of the coarser sediments could be deposited closer to the margin of the channel. In addition to all of that, you have other processes occurring. For example, if there is a lot of deposition in between the channels, so in an interchannel area, you could have very significant oversteepness. So you could create more mass transport flows or more tubiditic flows, and you could even get self-sustaining flows in this area. In addition, you have a lot of pelagic settling happening in the background, and this is even one of the most important processes because it provides a lot of the fine-grained sediments that we see, and that we see not only in mixed systems, but also chondrites and turbidite systems as well. So we end up with a setting where we create features like this. We have a mixture of erosional features, several channels that could be oriented downslope, and several depositional features that you see here with less bright amplitudes. And this case is taken from Uruguay, from the Cretaceous record. In addition, you can see that a lot of the sediment that is being carried laterally also can derive from the depositional features as well. You can see that there is a collapse of the flank here, but also some of the shapes that you see here of the sediment deposition, which is related to the current pirating fine-grained particles. So it's a quite specific setting, but quite often it occurs a lot in the deep ocean. But what types of mixed systems do we really have? Well, in the past, I had the luck to be able to work with different systems, different margins, and also to talk and discuss a little bit with other colleagues that worked in other systems. And together, we put up a model to represent all the different systems that we saw. And when we started to look into their variability, not only from proximal to distal, but also, for example, in the dimensions that these features have, in their orientation, and even the type of sedimentary phases that can occur in them, we realized that they could be somewhat classified. So we identified that there were systems, mixed systems in particular, that were more chondrite dominated, systems that were more synchronous systems, so where the two processes are more balanced, and systems that were more turbidite dominated. And I will show you examples of each case so that you have an example to look into, and something also that you might use to discover other mixed systems when you look at your own margins. So for the first case, for chondrite dominated systems, a lot of the thing that we noticed was that, for example, some of the depositional features, here you have a case in the US Atlantic margin, and a lot of people might know that this is very close and even includes part of the Chesapeake Drift, and the submarine fans and the channels that cut through it. So in this case, you have depositional features, and you can tell right away that instead of being oriented downslope, like what you see in a turbidite system, for example, they're oriented along slope and sometimes oblique. Here you can see the same thing as well. Another thing that was quite clearly noticed was that the channels that occur in chondrite dominated systems are also being forced to contour around these depositional features. So that quite often they will not cut through the thickest sediment deposition that we have here, so the mounded drift, and they will also contour around. And because of this forcing of the channel geometry, you might end up with several ponded turbidites in the channel. In fact, a lot of the sediment that comes down slope could be even taken into building the mounded drifts, and that way you don't form significant submarine fans. In addition, if you look at them into the seismic line, you can tell right away that their geometry of the mounded drift is quite similar to what you see in chondrite systems. So they are vertical, grading stacks. They might prograde a little bit at slope, but they do not shift laterally or downslope like you see in other cases. And this is particular for contrite-dominated systems. In addition, because the current is considered stronger in these types of systems, what you will see is that more often than not, you'll probably have synchronous interactions and even phased interactions. But the synchronous interactions is mostly the bottom current, parenting a lot of the sediment. And in the phased interactions is that we still have a bottom current as well occurring in this area, while there are breaks in the turbidity flows. And that's why we end up with morphologies that are more similar to those of contrite systems. Here you have a thickness map of the same system, so this exact one, and you can see where there is a main depositional and the channels that cut through it. Now, if we go to more synchronous systems, so we are talking about cases where we think that the two processes are more balanced. So there are not so much breaks in one or the other, and one will not have a very high or very different velocity than the other. We start to have slightly different morphologies from the previous one. The first thing that most of you will notice right away is that the morphologies are gentle, but also much smaller than before. In addition, all of them are migrating laterally towards one direction. So both the mounded drifts that you have here, these small lenticular shapes, and also the channels as well, which have less amplitude reflections than before, and also that they stretch laterally from the channel into the drift. So there's this whole pattern, this stacking pattern that occurs in these types of systems. Well, what do they look like in a map? Well, they are no longer oriented along slope or oblique. They are quite often oriented downslope. So this is the map of this exact horizon that you have here. And this case is from Nova Scotia, from one of the margins that I've worked on. And you can see that the features grow considerably in thickness in the middle, and then they lose and taper off. In addition, you will see that the channels in between follow the same orientation, but they are quite linear. So they are not as sinuous channels as we saw before. And they are not sinuous channels like you see in turbidite systems. They are quite linear, and also they become more unconfined further outward. So this is quite characteristic for them. In these systems, in addition, we will see both synchronous and phase interactions, and we can even tell this from the seismic, because, for example, this reflection here, you can see that it stretches laterally into the drift and that it loses amplitude and thickness, and that tells you that some of the sediment that was brought during the turbidity flow that deposited this one reflection was captured and transported laterally. So we had a synchronous interaction happening at this time. And that will occur throughout this type of system. But what about the other end? So the more turbidite-dominated systems? Well, as the name says, its features will be more similar to what you see in turbidite systems. So for example, you have here an example from the Weddell Sea, where you can see that you have two levees. You can see that their shape is much more cuspate. So they are no longer gently mounded. They have quite steep vertents, particularly close to the channel. And before, you only had one drift next to one channel, and then the next drift was associated to the next channel. So this is quite different because you have two levees laterally from the channel. In addition, you will see that they are oriented downslope, such as the map that is shown here. And this is another case of a turbidite-dominated mixed system, but at the present seafloor of Nova Scotia. And the most particular thing that you will notice is that one of the levees is much thicker than the other. In terms of thickness, in terms of height that it reaches, is much bigger. And this is because the bottom current not only winnows sediments being brought by these channels, so that from the turbulent clouds and distributes laterally, but also takes and reworks some of the sediments from this levee that is on the other side and deposits here. So it strips and winnows some of the sediment. In addition, you will see here that the channel no longer follows the same unilateral pattern of migration, so it does not have a clear pattern of following along as the drift used to do. No, now it's the channels and the coarser sediments in it are much more distributed, because here the current is much weaker. In addition, here, the turbidity flows or the gravitational flows are much more prominent, so we will have maybe coarser and maybe thicker sand deposits deposited within the channels. And in these cases, they may not stretch laterally like they do in synchronous systems or in contrarite systems. If we go towards the end of such a system, so we are still in turbidite-dominated system, but now we are going towards the deeper part, towards the submarine sand, we can also see different types of features being formed and being affected by bottom currents, but by much weaker currents. So the currents will not affect their shape as much, but maybe they will deviate it. So here we have an example from Shenglingong that was recently submitted, and you can see that there are several entry points in this case, and you have several bright amplitudes marking the position of several lobes and the channels connected to them. You will see furthermore that a lot of the lobes that derive from this entry point over here start to be deviated towards along the slope. And this deviation is being caused by a current sweeping to this area and taking and pirating the edges of the lobes, some of the finer particles that they have around them towards the extremities and spreading them laterally. So we still have a submarine fan and lobes, we should say more specifically, that you can still see its morphology, but its morphology is being slightly deviated towards along the slope. And that tells you that you are still in a mixed system, yes, but more turbidite dominated, because the lobes have not been completely reworked. So they have not disappeared from the record, and they have not transformed into contrarite drifts. So you can still see their shape. But what type of deposits do we see within all of these features that I've mentioned? For example, we have several models, not only my model, but models from other people that I've mentioned here. For example, for Marco Fornesu and his colleagues in ENI, for Emiliano Muti and Carminati. And all of these people, and some of our own work and even other groups, took a look into some of the sediment cores that occur in mixed systems to understand a little bit better how the processes that form them interact, and also how the deposits look like when within these systems. One of the things that we tried to do was look into the deposits that may occur within channels, but also more laterally and even more distally, to see if we saw differences in the sedimentary phases. And the first thing that we noticed, for example, when we took a look into some cores that were within the channels, we noticed that there were several phases that were more similar to what we saw, for example, in turbidite systems. So here I have some examples from my work and from other works, like I mentioned. And we noticed that there were, for example, convoluted beds or tilted and very distorted beds of not only local material, but material that was deposited before. And you can tell that these more than likely correspond to slides and slumps. So we have mass transport deposits occurring in the channels. We also saw that we had phases that could have a very large class, more rounded or more with sharper edges, and it could be very convoluted. They could be more mud supported, the cases shown here, or they could be more class supported. So we had paraconglomerates and orthoconglomerates. So we knew that we had the brights for sure. We also saw that in some of the channels, when you had breaks from these events happening, we could have deposition of finer beds in between. So the background sedimentation, which would form hemipelagites, pelagites, or in a finer contrarites, when there were no turbidite flows or gravitational flows occurring, and we could have this interaction. But when we started going more towards the depositional side, so further away from the channel, we started to see a shift in the sedimentary phases. And here I have put several examples. So for example, in the first case that we have here, we noticed that some of the coarser beds, which could have erosional bases like you see in a turbidite flow, or sharp bases as well, would have coarser grains at the bottom, but then they would fine upward, which is what we see for example, in the turbidite model of Bowman. But then they would course upward again, and there would be no sharp contact in between, and then fine again. So we realized in some of these beds, for example, you can see this here again, because it's coarser here, or finer, should I say, and then it coarsens, and then it fines again. Here there were some sandstones as well, which have different characteristics. So all of this was telling us that this grain size was changing throughout the core. So no longer did we have just a single event bringing a lot of coarse material. We started to have a change in the way that the sediment was being deposited. In addition, we started to see the presence of laminations, cross laminations, like you see here, some low angle ripples as well. And even here as well, you can see several ripples occurring throughout these sediments. And this all tells us that the bottom current is most likely dominating over this area, because not only did we have the original turbidite bed, but we started to see a change in the grain size. So all these changes, so for going from finer to coarser and then finer again, seeing these structures throughout the beds was telling us that another process was starting to affect the previously deposited sediment. In addition, we started to see more the dominance of more chondrite beds. So they would have not only these laminations, but also more bioturbation would start to appear the more we were here. And there was more sorting. So we were getting into an area of a mixed system where the bottom current was more dominant. And then when we got into the more distal part of the system, so we were not only going away from the main pathway of the turbidity flows, but also away from the main core of the current, we started to understand that there was a predominance of finer particles. And this is, of course, the pelagites, the hemipelagites, and even very fine chondrites that we see. And you can see that these phases are quite different from the previous one, because their contacts are more gradational, bioturbation is much more abundant, and we don't have as many structures as before. We don't have as many coarsening upward sequence or erosional bases. So we were much finer material the further outward we went from a mixed system. So we could tell that there was a change in the facies from going from the channels, so where we have axial faces, going towards the margins and the drift, and then further outward. And all of this was done thanks not only to my work, but to other authors and co-authors' work as well. Now, why is it important to study all this? Not only mixed systems, but you've seen here today as well, chondrite systems and the bottom currents associated to them, also other oceanographic processes like internal waves. All of this is important for a number of reasons. Most of you already know that chondrites can be very important because they can record and preserve the paleoceanographic changes and climates, but also there's other factors to consider as well. For example, the occurrence of submarine geohazards could be more propense to occur in these systems in case there is more sediment accumulation. For example, we should consider the fact that they are also important for deep marine ecosystems, because these currents could bring oxygen and other factors that are important for the macrofauna, but also for the economic potential, the carbon cycle, microplastics, and much more. In fact, during the last couple of years, I've heard many other factors to consider and many other applications for mixed systems than the ones that are mentioned here. But since we only have a very short time, I will focus on the first four, and just to give you a couple of examples for each one. So first and foremost, most people that study chondrite systems, of course, study them in principle because they can tell us a lot about a continental margin and its deposits, but also about the paleoceanography of that margin. Here we have an example from the Antarctic Peninsula. You can see here the slope, even some of the islands that are near the Antarctic Peninsula. And further downwards in the continental rise, you can see several drifts here and several tributary networks that go into deeper depressions, which are the channels that are in between all of these drifts. I put here a line that crosses right through this drift that you can see here. And you can see that there is a very thick sediment accumulation occurring here. In addition, you can see that this sediment accumulation, so the amplitudes of the seismic that you see here, has a pattern. You see that there are darker reflections, then lighter, then darker, then lighter, then darker, then lighter. And even at smaller scales, we see the same again. So there is a cyclicity. And this cyclicity is not by mistake, actually. When we took a look into the core that crosses through this sediment drift, so site 1096, and we compared its ages to the patterns that we see in the seismic, we realize that these patterns can be correlated to the marine isotopic changes. So to the changes between cold periods, marked here in purple or dark blue, we could say, and marine isotopic stages, marked here in this more greenish color. And you can see that the patterns, which were darker, lighter, correspond exactly to these changes that we have here. So we knew that the deposition of these sediments, so the process that drives the deposition, is tied to climatic changes. And we even look into the eccentricity, the obliquity, and the precession, and we realize that there is a very tight link to the eccentricity and to the pattern that it corresponds to. So because it is in the Antarctic margin, and because this is in the southern pole, a lot of the currents that sweep through this area are actually cold currents. And what does that mean? It means that they are stronger when we have glacial cycles, because we have more sea ice forming over in the areas closer to the shelf. And the currents then, the water mass that is associated to these currents, it becomes much denser, because the sea ice, when it is formed, then you have the water mass below much denser being formed, and it descends. And so during the periods, which are glacial periods, we will have more cyclic deposition at that time. When we look into one of the cores, so we took a look into, if I'm not mistaken, core 18, which is, I think, around here, may not be represented in the figure. I don't see it at the moment, but it's around here. So it's in the extremity of the drift. And we compare some of the ratios of the elements. So we have here, for example, zirconium aluminum. You can see it's between 0 and 2.5 meters. We noticed right away that some of the coarser beds were occurring in certain intervals. And I've highlighted here the intervals on purpose already, and compared them to the marine isotopic stages through dating. We realized right away that the coarser beds, so not only the turbidites, but also the reward turbidites and the chondrites were occurring during glacial periods. And then we had much finer hemipelagic sediments occurring in between. And this is because during glacial cycles is when the current was stronger. So that's when it was more capable of pirating and reworking the sediment laterally throughout the margin. So there's a very strong link to the climate in this case in particular. But climate is not the only thing why we look into these systems. A lot of people that look into mixed systems and even in chondrite systems also consider their potential for submarine geohazards. As you know, there are a lot of underwater cables, submarine cables, and other infrastructure throughout the ocean, for example, wind farms and other things along the shallow shelf, which are affected by some of the processes that form mixed systems and chondrite systems. So here we have an example of such a system, and this is in Brazil, published not that long ago, where we can see that the continental margin on this side is much more gradual and more gentle, and it has some scours that follow along the bathymetry, while on the other side, we have a much more rough topography cut by several furrows, and which become channels. So there's a very big dendritic network on this side, and which then flows towards and forms several submarine vents. So here, where we have the interaction between these two, we have a mixed system occurring. And you can see right away that the presence of these downslope flows, but also the along slope flows, causes a lot of erosional features. And all of these features can be very significant for the presence of submarine geohazards, and to take that into consideration. In addition, most of you know, for example, that contrite systems, such as the ones that are formed in the US Atlantic, and even for some of the mixed systems that we have in this area, they are often associated to a very steep slope, and that very steep slope has a gradient and an oversteepness that could generate more geohazards in the area. Here in this work that was done a couple of years ago, they marked the presence of several landslide scars that you can see here in red, but also the size of the mass transport deposits that are associated to them. And you can see that they are quite recurrent throughout the area. In addition, the more sediment that we put into these systems, in particular under-consolidated sediments, which can get to very big thickness and which can have a lot of water in the pore content, it could generate more slope failure, because you are putting, you are creating a significant thickness and a significant gradient over these slopes. So contrites themselves, the sediment itself, can also aid in the generation of slope failure. Now, bottom currents are not just something that erodes sediment and reverse sediment. They also have a lot of properties that are good for deep marine ecosystems. For example, contrite currents could bring nutrients, they could bring oxygen, which would be very good for the organisms and the macrofauna that exists in the deep oceans. Here we have a drawing of the different trait fossils that can be made by such macrofauna in the deep ocean, and you can see that they can vary significantly from more proximal to more distally, and even in the different types of deep water systems that we have. For example, there was a case study done in the Gulf of Cadiz, where you have several ridges and even several mud volcanoes, where they studied the presence of macrofauna, so the different types of organisms that you can have in these systems. And they discovered that there was a lot of corals and even cold water corals being formed throughout these areas. Here we have some examples. You can see, for example, many deep water cold corals, but also sea anemones, sea stars, sponges, and many other types of organisms that occur throughout these systems. So the currents not only pirate and winnow sediment, but they also bring nutrients that are very important for the macrofauna and the benthic organisms that are in this area. In addition, they can bring organic matter. For example, in this case here, they studied the presence of organic matter in proximal to distal settings, and they realized that in more proximal settings, the current would bring more organic matter, and also it would be buried much quicker. So the organisms and the trace fossils would be much shallower, while in this case, which was much more distally in the ocean, there would be less, and it would be more propense for deeper organisms to burrow and to create their trace fossils. So there is a variation depending on where the core of the current is and where it reaches the properties and the characteristics that it brings. Now, finally, most of you that work in industry know that there is an important economic potential for these systems. For example, not only for hydrocarbon exploration, but also for carbon capture and storage, and even for the discovery of mineral deposits, such as phosphate-rich sediments or iron manganese nodules. This economic potential was already starting to be discovered when they realized that there were some beds in contrite systems or mixed systems that had oil or condensates in them. For example, the case of Southwest Brazil, that some of you may be familiar with. But it was really propelled forward when Marco Fonesso and his colleagues published a paper in 2020 on the Mozambique margin. And in this paper, they revealed that in a mixed system, in particular in the coarser beds that occur in this mixed system, a lot of sand was being deposited. So they had over 100 meters of sand. You can see here in the logs how thick the beds were being deposited. But also they realized that all of the finds in this system were taken laterally and pirated by the bottom current. Hence why they had such thick sand beds accumulating here in this area. So the occurrence of the two processes together, not just one, created a very good reservoir, a very good gas reservoir, which is known as the coral and the mamba fields. And they had a very impressive net to gross ratio. So almost, I think, 92% was the results that they got from the course. In addition, they even did simulation to check where the coarser beds were and where they were less coarse, and they realized that this high net to gross body would occur along a channel, but that laterally a lot of the finds were pirated away. So the occurrence of the two processes was very significant for hydrocarbon exploration. But this is not seen just in this example that I've shown you here. In fact, there are other cases, like the one shown here from Uruguay, which I showed you at the beginning, which also have very high amplitude reflections within their channels, and which correlate quite well to the high amplitude reflections that we see here in this case. So more than likely, we have a lot of coarser sediments being deposited in the channel, and by having a current sweeping through and pirating the finds away and depositing it in interchannels, we might be creating a potential play here, which could be very significant. And that is why I was showing a little bit of the implications, just to present you a little bit of mixed systems and the work that we have done. Thank you.